So, so let us recall what we have said in the last lectures, and well, I will recall the following. If we have a measure, then this is a measure is the spectral measure of a Jacobi operator if and only if we have this normalizing condition, and then all the polynomials are in L2 are mu, and these polynomials are dense, and they are dense in this space. Okay, so we have this assertion. Okay, and we also define the Weil M function. Was defined as a function given by the action of the resolvent to the first element of our basis. Okay, and we already know that this is just the integral of this expression, and this is a Hergel function. Okay, this is a Hergel function. Alongside this function, we have the so-called green function, and this is just this expression, and we also have that this is a Hergel function. I remind you that a Hergel function is a function that, by definition, if z is in the upper half plane, then the function evaluated at this point is in the upper half plane. Okay, and actually, it's interesting that these simple conditions, this simple condition with which defines a Hergel function, has a lot of consequences that will be important for us in the following. Okay, so we have this, and we have also a formula for the green function. We have a formula for the green function. Okay, this formula is the following. Well, I'm writing it a little in a different way, but it's just the same. Bn squared n plus bn minus 1 squared n minus z plus z minus qn. So we have this expression, and well, I also remind that we have our matrix, which has 3 diagonals and extends here to infinity, and we have performed some kind of we have here 4 points, 5 points here, and we have a finite matrix here. So we have a finite matrix here, which is denoted by Jn. This is the nth place, and this is Jn minus, and this is Jn plus, and respectively we have the m-Weil function, or the Weil function, denoted in this way and in this way. Okay, and so these Weil functions are the ones that appear in this expression. Okay, so we have this situation, and actually probably I will write the following. This expression will this expression yields the following. I just copy this one, z minus qn, and this is a Weil function multiplied by a positive number, and we have also here the same situation, but this Weil function corresponds to a finite Jacobian matrix. So we have and let us do here the following assumption. Let us denote it by H1, which is hypothesis 1. I will consider that the essential spectrum of the Jacobi operator, which was denoted by A actually, the essential spectrum of the Jacobi operator this is the original Jacobi operator, or in the case that the operator is not self-adjoint, this is just a self-adjoint extension of our operator. So just as we convened in the previous talk. So we are assuming that the essential spectrum is empty. So we only have discrete spectrum. This means that we have a sequence of eigenvalues which do not accumulate in any real point. Okay, so we have real values with no point of accumulation. Okay, so assuming this and taking into account this expression for the m-Weil function, it is not difficult to say that to verify that then the Weil function can be written just as a sum of weights. Let us write these weights as follows. Here we can put alpha k minus z, and the sum is for all alpha k in the spectrum of A. Okay, so these of course are the poles of the Weil function, which are actually the eigenvalues of operator, and we are taking all the eigenvalues of the operator, and these can be the weights. These are the weights of the function. We of course know that this measure is related with this sequence of points in the following way. There is a function. Well, I'm denoting the function that is related with the measure by the same letter, but I hope that this won't lead to any confusion. So we can write this alpha k less than t, and here we have the weights. Okay, so this is a function which has a jump in the point alpha k. This is alpha k plus 1, and here we again have a jump. This function, I think, was written in such a way that it is continuous from the left. It could be continuous from the right. It is the same. It all depends on your political orientation. But actually, this as we know, if you have a function which is monotone, a monotone function continues from the right in a one-to-one correspondence with a measure, with a Borelian measure. And so in some places I will just consider the function, not the measure, but it is just the same. Okay, so if we have this expression from the Weyl function, then since this is a Weyl function and this is also a Weyl function, I hope that it is not difficult to see that we can write this in this way, where this eta k is the weight is the weight given by either by this Weyl function or by this Weyl function, okay, multiplied by these constants, okay. So we can write the green function in this way, okay. This will be important for us in the following. So I will recall you that we are trying to solve the following problem. Okay, we are trying to solve the following problem. So we have a matrix and a perturbation of it, which is given by this matrix. This matrix corresponds to changing the end spring constant and the end mass, where this theta and h are related with the increment in the mass and in the spring constant by these relations. Okay? So, okay, let me skip this thing. Okay. So, actually, it is not so difficult to study the direct problem. So we can solve the direct problem just by considering the quotient of j of z and j tilde of z. Yes, if we consider this and take into account the properties of these functions, then we can just by studying the distribution of zeros of this quotient, we can understand how the the relative distribution of the eigenvalues is, what the relative distribution is. And in the case when we perform a perturbation just in the first spring without modifying the first mass, then it turns out that for the analysis of this situation, we can just consider the quotient of the m function and m function corresponding to the perturbed system. And then this quotient is also a Hertzlos function. And the zeros and poles of this meromorphic function are just the spectra of the unperturbed and perturbed operator. So we have this situation. It is easy to see that there are interlacing between the spectrum of the original system and the spectrum of the perturbed system. There is just interlacing of the spectra. And this is a simple consequence of the fact that this quotient is just a Hertzlos function. Okay? Of course, we can consider more difficult situation, and then we perform perturbation of this kind. We not only modify the first spring constant, but also the first mass of the system. And then we again study the quotient of these green functions now. And now this is not a Hertzlos function. So we won't expect any interlacing. There is no interlacing anymore. But we have the following interesting situation. We have that the spectrum is somehow attracted to this constant gamma, which is defined by theta and h. So this constant gamma is defined by our parameters of perturbation, and it works like an attractor of eigenvalues. This point attracts eigenvalues. Of course, if we consider the situation in which theta is greater than 1, which is a decreasing of mass, in this case, I think, if I'm not wrong, this means that the increment is a negative number, then the point gamma works like a repelling, like a thing that repels eigenvalues. So we have this interesting situation in which when theta is less than 1, the point gamma acts like an attractor, and when theta is greater than 1, the point gamma acts as a point that repels the eigenvalues. Okay, so okay, in the general situation, well, this was the case when we perturbed just the first string and the first mass. But now let us perturb any mass and any spring constant. If we perform this, we have a very similar situation, but we could have intersection of eigenvalues. Okay? Well, I'm actually not telling the whole thing, but the main difference is that we can have intersection of eigenvalues apart from this point gamma. Okay? Okay, so this is well, here is just some of the things I was just saying about how we can determine this these relations between eigenvalues. And here we have an interesting formula. Recall that if we consider the green function of the perturbed system, then we have to change this by the corresponding one and this by the corresponding one. And if you make the calculation from this quotient, it is just this expression. But this expression is cardinally different from the one that we had before, because as I mentioned before, if we consider, for example, this quotient, we have this is a Hertzsprung function, and well, depending on the sign of this function, it is easy to see that this one is also a Hertzsprung function. But in the other case, in this case, we have here a Hertzsprung function. This is a Hertzsprung function, but this is multiplied by z, and this changes all the picture. That is why we have this a much more complicated distribution of eigenvalues. Okay, so well, this I will skip, I think, this. Okay, so okay, let us now consider the inverse spectral problem. Let's now consider the inverse spectral problem. Well, oh, sorry. Let me see if I have this this expression here. Yeah, I have this expression here. Okay, so okay, let's consider the inverse problem. So suppose we are given the two sequences, and these sequences are the spectra of the system and the perturbed one, and it is actually not very difficult to show that we have this interesting relation between eigenvalues. For example, this series is convergent, and also we have the so-called Crane representation formula for Hertzsprung function. This is this formula which is here, and on the basis of this formula, one can show that if you consider this situation, or this situation, or this situation, then the spectra determines completely this quotient in all the cases. Here we have interlacing. Here we do not have interlacing, but nevertheless we have always the same expression for this quotient, which is completely given by the eigenvalues. So the eigenvalues determine this quotient, and since we have these formulas, if we have this quotient, then we have this expression. And then if you know the parameter theta, and if you know theta, you can know h, because you know, well, if you know theta or gamma, then you can determine this function. And then you can try to reconstruct the matrix from this function. And I mentioned, not yesterday, on Friday, that if we know the Weyl function, then by means of the inverse Stieltjes transform, we can recover the measure. And if we have the measure, we already know that if we perform the Gram-Schmidt method of orthogonalization to the sequence of powers of the independent variable, then we can recover the coefficients of the matrix, the entries of the matrix. So, so the goal for reconstructing the matrix is to know the spectral measure or the M-Weil function. But if we only can recover this function, then we need to know these constants to determine these functions. And then if we determine these functions, then we can determine the finite matrix and the infinite matrix. Okay? So so this is the way this is done, but I want to show you that this is not quite straightforward. Well, I have 15 minutes for doing the following. Okay, let us see the. I will. Well, I think I have just erased what was supposed to remain on the blackboard, but okay. Let me just okay. Okay. Actually, there are some nuances here that I especially deliberately didn't mention. But I think that the most important is the following. If you have this expression for the green function, then you have to decide. You already know that you have to extract from this expression a sum with n elements, because for this finite matrix you should have n eigenvalues, and then this sum should be decomposed in two sums. One sum should be finite with n elements, and the other sum should be infinite. Okay? But you can do this in different ways. And you can, for example, take, if you do this in one way, you can take one element of the sum here and put it here, and then take another one here and put it in the first sum. Okay? So the important thing is just that you have to have n elements in this sum. So actually there are more than one solution of the inverse problem. It depends on how you distribute this sum, and here I'm deliberately being not very precise, but the idea is just playing with this distribution of terms in the sum. And but there is the important thing here is that this sum should be always a sum that corresponds to a Weil function, to the Weil function of an infinite matrix. Okay, and this is not not quite easy to do, because one of the conditions for this let us write here n with 2 tildes, that Ithaca with 2 tildes should be this sequence should be such that if one defines a function which is actually a measure, in some case I want to specify what, which, so that this function and the measure is such that all the times the polynomials are dense with respect to rho, the function rho, because this thing corresponds to a measure which is related to a Jacobi matrix. So the polynomials have to be dense in this space. Okay, so the polynomials have to be dense in this space, and this is a point where we need to be very careful, because it turns out that if I have a measure from which such that the polynomials are dense with respect to this one, and I take away, well, not take away, put, for example, if I have a measure mu and I add just a point mass, where this is the point, the discrete measure that gives weight only to the point x, and we suppose that x is not in the support of mu. Okay, and mu is the spectral measure of a Jacobi matrix. So this, for this space, in this space, the polynomials are dense. Okay, but it can be proven that in this space the polynomials are not dense anymore. This is quite surprising, actually, because we are just adding a point mass to the measure, and automatically we can destruct the density of polynomials. It is actually counterintuitive. We cannot expect this, but this happens. I can prove, I hope. We're not... I hope to prove this, but now I'm just telling you that we have this situation in which for this measure we don't have density of polynomials, and then our game of distributing eigenvalues here, putting a term of this sum here and then changing here, it's not quite clear if we can preserve density of polynomials in the infinite sum, but we have to preserve density of polynomials all the time. If we have that this this part of the sum corresponds to some Weil function. Well, and well, okay, but then it happens another kind of magic here, because okay, we know that we can destroy the density of polynomial just by adding a point mass to this spectral measure. But at the same time, we know that if we add a point mass, it actually does not matter if this point, well, let's consider that the point x is not in B. The point x and y are not in the support of mu. But if I add a point mass and then, oh no, this should be in the domain of in the support. Y is in the support of mu. If I add a mass point and subtract a mass point from this one, then automatically this new measure again is a measure such that the polynomials are dense in the corresponding space. So if we denote it by hat, then the polynomials are dense this space. So here we have a very important remark that actually it seems that we firstly it seemed that we can freely choose which elements will be in the finite sum, and then we observe that if we just change one point mass of the measure, then we could be in problems. But actually all is solved by this interesting result, that if you subtract, you can add if you subtract one mass point of the measure, and then you can preserve the density of polynomials. Okay, so let me see. Well, actually I have run out of time, but well, let me stop here then. Do you have any questions? Yes, you just have to put any positive numbers. It's, the question of density of polynomials is a very subtle question in analysis. It goes back to the it goes back to the beginning of analysis. But it was a lot of work in the 50s and the 40s and 50s, and actually the main results that are known today are from the 50s and 40s, but now we are using these subtle results in solving inverse problems. Okay, more questions? No more questions. Well, Okay, so I'm thanking all the people for coming here, especially Margarita. She really helped us a lot. So let us thank Margarita for. And I want also to I want also to thank our invited speakers. So let us thank our invited speakers.